So in that initial video, Batman had two types of energy. So the two types of energy we've been talking about is mechanical and potential. At what point did Batman have the most potential energy? Well, it was at the highest point. And I guess in the diagram, it would probably be, I guess, here initially, where it was just starting. If we ignored friction, so ignoring friction, then number 5 would probably have a large amount of potential energy as well. If we don't ignore friction, then it was definitely number 1. You see that because Batman doesn't return to the same height. Maximum kinetic energy is present at point number 3. So at the very bottom, so where that potential energy is the least is where the kinetic energy is the greatest. And we know that there's also these points in between, and that's what we're going to look at this week. Last week we were already looking at potential and kinetic energy on their own. We're going to look at these points where there is both potential and kinetic energy. So that was point 2 and 4. So in between, we have points where there is both potential and kinetic energy. And that is going to be our focus this week. At those points, the total amount of energy is the same as point 1, point 2, point 3, point 4, point 5. The total amount of energy doesn't change. That's an important physics principle. That is the conservation of energy, is the physics principle that pertains to the ideas this week. And that's that the total amount of energy doesn't change. So at point 1, 2, 3, 4, 5, the amount of energy doesn't change, but the types of energy does. We've been looking at potential, kinetic, and those amounts being the same. Now we're going to look at those points 2 and 4, where the potential energy plus the kinetic energy is the same as the total amount of mechanical energy. Now the reason why Batman doesn't come back and hit my son in the face is because of friction. So we do say that the amount of energy is conserved if we ignore friction, because there are conservative and non-conservative forces. If we look at friction is a non-conservative force, which means that the total energy of the system is going to be decreasing over time. We're going to be losing that energy to heat or sound. So that energy is going to go away. So if we look at the amount of potential energy, so initially we had all potential energy, we had no kinetic energy. As the Batman swings back and forth, potential energy goes to 0, and then we get potential energy again, then it goes to 0. At the same time, it's being converted to kinetic energy. So potential becomes kinetic until I have all kinetic. And then that kinetic is converted back into potential. And it goes back and forth like that as it swings side to side. Now, the total amount of energy for this video for Batman is going to go down, because there is friction. So if there are non-conservative forces like friction, we are going to be losing energy to the outside. So we're losing that energy as heat. The total amount of mechanical energy does not stay the same. For most of the questions that we do, though, we're going to assume that the total amount of mechanical energy does not change. So the total amount of this energy of the system is conserved. So my potential energy will become my kinetic energy. So potential energy goes to 0, then goes back up. If we were to look at our kinetic energy, my potential becomes kinetic. Kinetic increases until the bottom where it's all kinetic, and then goes back to being potential. Now, these are the types of questions that we are going to be doing calculations for, where this total amount of mechanical energy does not change. So we ignore friction. We know in reality that it's there, but by ignoring friction, the analysis of these types of questions becomes a lot easier. So summarize, the total energy of the system is equal to kinetic plus potential. This is what we need to know to do the calculations this week. We are not going to be dealing with energy loss due to heat, but if there is friction and some of these non-conservative forces, then energy is not conserved. It cannot be conserved. But we're going to be dealing with questions in our imaginary physics land, so we're going to ignore non-conservative forces. So my total mechanical energy is kinetic plus potential, which is 1/2 mv squared plus mgh. So here's a question. Maybe pause the video and answer this question on your own, and then we'll do it together. So this is a system that's nearly frictionless. We have the cart starts from rest, and we want to find the kinetic potential energy at points W, X, Y, and Z. The first place we're going to start out is probably point W. At point W, if it's starting from rest, I know that it has all potential energy, which is mgh. I guess we need a mass. We'll say that this cart is 60 kilograms. Maybe it's empty. So my potential energy at that point is 60 kilograms times 9.81 meters per second squared times the height of 60 meters. So when it's all potential energy, so my mechanical energy at that point is all potential, which is 60 times 9.81 times 60 meters is 35.3 kilojoules. Or 3.53 times 10 to the 4 joules. So my amount of potential energy at that point is 35.3 kilojoules. If I were to look at point X, so point X now, this is the very bottom, this energy is going to be all kinetic. Now the amount of kinetic energy here is going to be equal to the amount of energy at the top. At the top it was all potential, at the bottom it's all kinetic. My kinetic energy at point X would be 35.3 kilojoules. At point Y now, I have both potential and kinetic energy. Now I have information here that I can calculate the potential energy. The potential energy at point Y is mgh. So 60 times 9.81 times the height of 25 meters. So my potential energy at point Y is 14.7 kilojoules. Now what is my kinetic energy at point Y? Well, I know my potential energy is that much, and I know the total amount of energy always has to be 35.3 if energy is conserved. So 35.3 minus 14.7 means that I have 20.6 kilojoules of kinetic energy at point Y. So at point Y, I have both potential and kinetic, and I have some more kinetic compared to my potential. I can do the same thing for point Z. My potential energy at Z is mgh, so 60 times 9.81 times 5. My potential energy is 2.94 kilojoules, which means that my kinetic energy is what's left. So my kinetic energy at point Z is my total energy. My total mechanical energy, which has to be 35.3, that amount won't change, minus 2.94 would be 32.4 kilojoules. Now we can use this to find the speed at point X. So we know our kinetic energy here. I also know that kinetic energy is 1/2 mv squared. So if I know this value is 35.3 kilojoules, and I know that's equal to 1/2 mv squared, the speed will be equal to my kinetic energy times 2 divided by my mass and then square root it. So I take my 35,300 kilojoules, I multiply that by 2, I divide by my mass, which is 60, and then I remember to square root that. And my speed at this point is 34.3 meters per second. So the big idea is this total amount of energy, here we found it at the start, is always the same. So the sum of the energy at all of these different points will be the same as my initial energy. Here's one more question. So I'm going to start where we have both potential and kinetic. So at the top here, I want to find how fast the motorcycle's traveling at the bottom of the hill. So what's my speed here? I know initially I have potential energy and kinetic energy. I'm going to say that's at point 1. And then at the bottom, I have no more potential. It's going to be all kinetic. Now I know that those amounts of energy are going to be the same. I'm not given the mass here. So I'm going to build this equation first. So my potential energy at 1 plus my kinetic energy at 1 is equal to my kinetic energy at point 2. So 1/2 mv1 squared plus mg, and the height at 1 is equal to 1/2 mv2 squared. Now I don't need my mass. I can divide by mass, so I can take care of that, and that goes away. Maybe I'll multiply everything by 2 to get rid of this 1/2. So I get v1 squared plus 2gh is equal to v2 squared. And I'll square root both sides. So the square root of vi squared, or v1 squared, plus 2gh is equal to v2. You'll notice this is very similar to a kinematics equation that we already have. But now we're building it using energy. It's the nice thing about physics, it's always the same. So 62 squared plus 2 times 9.81 times 20. I'm being careful with my brackets. And then I square root that. And I get a speed of 65.1 meters per second. So the big idea, the amount of energy at any point is equal to the amount of energy at any other point, but the types of energy might change. It might be just potential, it might be just kinetic, it might be potential and kinetic. But the total amount of energy is conserved.